minimum variance solution that has 0 expected error. So are we done? So is there any, or is there anything, should we always do the linear least square solution to find the line that fits the statement? If we're done, then everyone can leave for today and we'll come back on Wednesday. But I still have half the board to fill up, right? So there's probably some stuff that's we're not quite.
Well, you probably want to see if your coefficients are actually contributing to the model or not.
Okay. Yeah. So. So we'll get to this. It's a little useless coefficient. So this is something we'll come back to, and we'll figure out how to kind of do something that gets rid of useless coefficients. But in the case of 2D, this is already there really is only one coefficient, or maybe there are two if you count B. There's A and there's B. But this is so. This is something that we'll come back to with the lasso, and I'll mention this briefly today. It won't make as much sense in 2D, but in higher dimensions, this is a really important problem. But there's still other things which were. Still other issues with this. So what did we, I spent an entire lecture basically talking about these different distances. And maybe it was silly to spend a lecture doing that, but I think it's important to emphasize these different distances. Why? So why are we using the L2 distance?
Because the math works out the best in the L2.
Yeah, that's right. So that's why we are using the L2 distance. But can we minimize the L1 distance instead? What if we wanted this expression here, right? So let's circle this out, right? So this is the sum of these squares, but the squares kind of amplify outliers, right? So, and why do we care? If we look at all these green lines, why are we minimizing the square of all of them? Does that make much sense? Well, yeah, so it's easy to write down the math here, so it's easy to do this, but is it harder if we do L1? The L1 distance instead.
We have to use a linear programming package to do that, but it can be done.
Yeah, that's right. So you can actually do, there's something that will be kind of in between these two. So actually, if you use the lasso, you're kind of mixing the L2 and the L1 and the L2 norms, and you can avoid using a linear programming there as well. Yeah, but if you're minimizing the L1, you need you'll need to use a linear program. In low dimensions, you can actually, you can actually avoid using a package if you want to. Okay, so there's something else here. So there's 0 expected error. So what if, can we have less error if we add in some bias? Right, so this is an unbiased solution, but our goal was to minimize this error. But we restricted that at 0 expected error. What if we didn't do this? Can we get less error? And is that better? It turns out in some cases, yeah, you can actually get less error here if you get rid of this 0 expected error solution. And this is actually really easy to do. So we'll see how to do that. There's something else kind of unexplained that we did. So why are we looking at this vertical distance, these residuals? That's probably CAL, right? Yeah? Okay. I'm not the best speller. Okay, so if you look back over here, maybe I'll draw a new picture here. So we've got these data points, and we drew some best fitting line through these data points. And then we were looking at these vertical distances here to this line. Right, so if our goal is to have a line that fits the data, why are we not looking at the best distance onto this line? Right, you can have a shorter distance here by projecting to the closest point on the line. Right, so why are we using this vertical distance? So we can also minimize to the closest point on the line. And they'll actually be, this is actually also fairly easy to do. But there are going to be some very good reasons why we don't actually want to do that.
Well, couldn't you just rotate the data and get, close to get basically the same result?
Which way do you rotate the data? You need to know that ahead of time, because the slope of the line determines the direction of the projection. So,
but regardless of whether the projection is just going to be orthogonal to the whatever set of basis vectors you're using, so you could move the data into a different basis.
So it turns out that's actually what how you do this is going to work. So this is basically what PCA does, and PCA is all about figuring out how to rotate the data into a basis where you're measuring this vertical direction. So that's all we're going to do. We're going to rotate it into a basis where the natural direction is going to be or the closest direction is going to be essentially the vertical direction. But that's a choice of rotation. So how do you choose that rotation? So that's going to be the challenge. So it's kind of like choosing the slope, but it's not quite the same problem. It'll be a very different technique how to solve it, but it's also not too hard. And then the final thing is that this the matrix inverse this operation is expensive. Okay, so it's pretty expensive to do this operation, especially on really large data. So if you can avoid that, it'd be good. So can we solve this without doing the matrix inverse? So this will be more of a computational thing. And I won't exactly answer this. There are some techniques to kind of precisely solve this L2 problem without doing the matrix inverse. We'll actually look at some other problems and we'll solve those other problems without doing the inverse. You can use similar tricks to kind of get around this. But we probably won't solve the problem exactly. We'll have to make some approximations in order to avoid this. Otherwise, the problem is just as hard as computing the inverse. So we'll approximate what we're doing a little bit, but avoid this expensive matrix inverse. Okay. All right, so these are some interesting questions, and we'll spend regression I think is a really important problem, so we'll spend the next few lectures kind of addressing some of these as well as extensions into various extensions into higher dimensions. So some of these only make sense if you're in higher dimensions. So I'm going to quickly give a preview of several of these techniques. Board up. Before I go to the preview, before I do this, I'm going to talk about something that does not not exactly fit any of these questions. We're somehow going to avoid outliers in a certain way that wasn't directly addressed by any of these bullets. Okay, so we're going to talk about the Thielsen estimator, which is a different way of fitting a linear model to the data, but it's defined in a different way. It's not trying to minimize some sort of objective function, but it's got some different nice statistical properties. Okay, so who's heard of a robust estimator? So what is a robust estimator?
So one that doesn't change very much when it's how much your estimate changes versus how much the data has changed.
Yeah, that's
so robust means that I can change the data a lot, but my estimate won't.
yeah, so that's pretty good, right? So it's all the definitions I've seen have actually been a little bit vague like this. You kind of say that you want to find some estimator. Let's call this M of P. And so you say that if some alpha fraction of the data changes, and so by changes I can mean arbitrarily changes. I could say that some P1 in P goes all the way to infinity. I can take it, I can send it off to the moon. You know, it's a complete outlier. There's a miscalculation, right? You see data, and all of a sudden one data point says like 1,000,000. All the other things are between 1 and 10. It can go really far away. Then I want to say that M does not go to infinity. Okay, so I can't have my estimator move arbitrarily far away. So kind of I want it to stay within the data, within the rest of the data. And so alpha is some parameter, and you can say that, what was the exact term? Yeah, so alpha is what's known as the breakdown point. So how large can I make alpha? Can I make it? And the best you could possibly do is to move half the data away to infinity. Right? If you move more than half the data, you should probably move your estimator with it. Right? So if I said half my data is on the moon, well then I should probably put my estimator on the moon too. Right? Or if 2/3 of it is up there, right? Because that's where all my data is now. So like a classic example is like the mean of a set of points is not robust at all. If I took the mean, I take one point and I set it to infinity, well now my mean is also infinity because infinity plus some constant divided by n is still infinity, right? If I take the median of a set of points, well I can move up to half the points away, or just under half the points away, 1/2 minus epsilon, and my median is still within the rest of the data. Right? I can have these data points here. The median is going to be, say, this one. And now let's say I take this data point, this one, and this one, these four, and I move them way out here. Well, now my median is still the same data point. It happened I took half from either side, but I could have taken all these. The median is still in this range. And it doesn't matter how far away I move these. The median is not going to really move that much. Okay, so how do we do something, a robust estimator like the median for a line? So what's the right way to do that? How do you take the median of a line?
Median of each number.
Yeah, that's right. Yeah, so it's two parts, but that's basically it. You take the you define a set equals the slope ij for pi and pj in P such that Pix is less than Pij, Pjx. Right, so take all the points and have them in a sorted order, and then you define the slope between them. So the slope is x, was it the y distance over the x distance? I mean, so then this is yi, yj over x I, xj. So then this is the slope. I take the median of all these slopes. I say A equals to the median of the set S. And then I go back, and instead of solving B like this as the difference in the average, I essentially take the median to find the intercept as well. So in doing this, it's called the Thielsen estimator. This gives me an A hat, and you can get a B. So that this is the median of the y residuals. You probably can't do that, but it's just the median of the y residuals as well. And this is called the Thielsen estimator, and this has an alpha value, a breakdown point of something like 0.23. Got rid of the notes. So it's 0.293. Okay, so it's close to 1/3 or 293. So I can move almost 3/10 of all the points away to infinity, and this will still make sense. It's not the perfect one. I want to get this alpha up to 0.5, like in the median. The Thielsen estimator does not quite do it. This is usually the first thing people try for some reason. There's an extension by Siegel, where instead of this, what you kind of add an extra step. For every point, you look at all the slopes that it's part of. You take their median, and then you take the median of all those, and that gets you the A. And that gets actually a 0.5 breakdown point. And so that's a little bit better. So this is the median of medians. So I won't try and write this all up. But so there are these approaches, and these are also fairly efficient to do, and they will avoid these sorts of outliers that can really screw up a least squares estimate.
So if there aren't outliers, then this would return an estimate that's pretty close to least squares?
Yeah, if there aren't outliers, then pretty much whatever you do will give you roughly the same thing. Yeah.
So you said it's fairly efficient. Well, it seems, I don't know, it seems like it might be kind of difficult to do. I don't know.
Yeah, so it's a good point. I'm calculating n squared of these slopes, right, before I take the median. Or if in the Siegel I'm creating n squared slopes, and I break them into groups of size n, taking the median. So you can take the median in linear time. The data set, there's some algorithmic tricks to do that. You can actually do this in n log n time for n points. So it's a bit complicated to do it, but you can get this a fairly efficient implementation of this. The naive way, you're right, is going to be slower than doing this. Although, yeah, you can avoid a matrix inverse in 2D. So, and it's a bit more complicated in higher dimensions, but you can do something kind of like this as well. But mainly people do this in 2D. And there's probably packages out there that will do this. I know there are some packages that will just minimize the L1. If you minimize the L1, this is also going to be a robust estimator as well. We'll talk a little bit more about what L1 means in a later lecture, or actually maybe later in this lecture. All right, so this is the Thielsen. So this is another option that if you're worried about outliers, then you could use this. There's something else called Tikhonov regularization, or this is sometimes just called bridge regression. And so this is a very different approach to dealing with outliers. So instead of minimizing just the L2 distance, I'm going to minimize L2, I'm going to call this alpha. Okay, where it's going to be the sum of py minus a px minus b, and then I'm going to add on this extra term here, alpha. A squared. Yeah, so actually let's, just to simplify this a little bit, let's assume, I'm going to ignore this, I'm going to assume equals 0. So I'm going to assume that all the x and y coordinates have been equal to 0. That's not true. I can go and subtract out the mean of them pretty easily. So instead of minimizing this is squared. So instead of just minimizing these squares, I'm going to add on this term known as a regularizer, or this is the regularization term, and this is okay. So I still want to minimize this expression, but now I have this extra penalty term. And so alpha here is going to be a constant. Alpha is a constant that's part of my definition. And we'll talk about how to choose alpha a little bit later. But, so what is this saying? This is A, which is the slope of the line. So if the slope of the line gets large, then I have a larger cost. So this is biasing me towards having a smaller slope. Okay, so why would I want to do that? So let's draw a picture here. So let's have our simple picture of these data points here. And they go through, I've centered the data points. And so I've written this here without assuming this, but if you don't assume this, then you put like you kind of use this, you can extend this to higher dimensions and use this trick by putting the 1 here. So, okay, so if I have my regular least squares, I'm going to get something that looks like this. And now the result of the ridge regression is going to be something with the smaller slope. Okay? So I want a smaller slope here. It seems like it'd be an odd thing to do. But this is going to be more robust to outliers. So the thing is, I've assumed that one of the assumptions I made when I'm looking at this vertical distance here is that all of the data is, I know the x coordinates exactly. This is kind of given to me. And all the noise is in the y direction. Okay? All the noise is in the y direction. And so now if I have an outlier point, the outlier point is probably going to be like really far. If it's an outlier, it's very different in the y direction, right? It's very different in the y direction. It's going to be way up here, or it's going to be way down here. So if I've got a point that's way, way down, so I have a point that's way down there, what is this going to do to my slope? It's going to make the slope really large, because I'm going to have to try and account for this data point down here. So if I want to correct for that, I kind of want to say, well, let's try and not make my slope too large. Let's kind of bias towards having a smaller slope.
Outliers can be in other way also. I mean,
It can also be high, yeah, but if it's not too far from the data, it doesn't matter so much. I'm averaging over a lot of data. If it's an outlier, it's really far from everything else. Right? If it's not that far away, it doesn't matter. If it's really high up here on the left side, actually the slope is going to be like this. It's going to be opposite that I want.
I mean to say, the outlier can be in such a position that it will try to put the line in the other direction.
Right, yeah. So let's say that this is like 10, this is minus 10, and now I have one data point here, and it's all the way up here. Let me write this in green here, right? Right. So this is the x-coordinate is minus 3, and this value is, is like 10,000. Okay. So now, how's my line going to fit through here? The line, my least squares fit line is actually probably going to look like this.
Your outlier can also be 10,000 and minus 3. X
Oh, and the x, yeah. So under the model of all this stuff with regression, I'm going to assume the x-coordinates do not have noise in them. And we'll discuss a little bit later why that is. But the model is all the noise is in the y-coordinates.
So even if there is a noise only in y-coordinate can be really less, which will bring the line down.
Oh yeah, so you could have a point that is a small y and a small x-coordinate. And if it's along the line of everything else, then that's fine. If it's off of that line, then that's a problem. So part of the model of these linear fit is that everything should lie close to a line, so that if the x-coordinate is really large, the y-coordinate should be really large, as long as the slope is positive. As the x-coordinate grows, the y-coordinate should grow at some fixed rate. That's our assumption that we're trying to fit a simple shape. In this case, we're trying to fit a line. It needs to have that property. That's the assumed model. If that's not right, if that's not the right model, maybe you want to do a second order polynomial. Maybe you want to do something else entirely, a different class of shapes. But to simplify our discussion, we're talking about just a line through two-dimensional data. So, and really, if that's the case, we're assuming error in the a lot of error in the y-coordinate. That's the outliers we need to worry about. And so those are going to cause the slope to be large. So you'll see some pictures, probably most times when people draw pictures of outliers, say like on Wikipedia. So first of all, keep in mind that I'm drawing these pictures in 2D to illustrate points. Most data is not going to necessarily look this clean, right? You're going to get, your data may be in higher dimensions, it's not going to be centered around 0, it's going to be kind of bunched up in certain areas. And a lot of pictures, like on Wikipedia, will do something where you have data like this, and right, and so the line you want to fit is here, and then there's going to be one outlier point, and they're either going to draw the outlier point down here, or they're going to draw it up here. So why is that? Well, they do that because they want to draw a nice graphic that fits the square, and the easiest way to draw an outlier is within the square the data is already in. If you draw it all the way up here, then the data kind of gets scrunched a little bit to fit in the same space. So you're probably used to seeing outliers that always kind of fit in the square of the data. And that's because of this bias towards drawing these pictures. There's no reason why it has to be down here instead of way up here. But either way, if it's really here, it's kind of within the shape of the data. And maybe this is an outlier, maybe it's not such a big deal. But if you have enough data points, one point down here is not going to really cause the line to shift much. It's probably, if you have like 100 data points and one data point is off by a factor 10, you may shift the line a little bit like this, but it's still pretty much capturing the data, and that should probably be fine. If you have a rough capture of the data, that's really, for most cases, you don't need the absolute best thing. If you can solve for it, you might as well do it. But an outlier this far down one outlier down here is not going to be that big a deal. If you have a bunch of points right here, well, maybe you should pull your line down because there's something else going down here. Or maybe you should really be trying to fit a different model than just a linear fit to it. The real bad case, and this in actual data, what you'll see is you'll get a bunch of these measurements, and probably some of you are doing this with the data you've collected for your projects. You'll have some spurious means, which are just some number which is completely ridiculous. And that's going to be like way up here like this. You're going to get data like this. And this is what you want to avoid. And so that's why the Nielsen estimator and so forth will be completely robust to that. This is kind of going to bias away from this sort of thing. And in fact, a small constant here, we'll see, will actually do a pretty good job of worrying about those sorts of things.
I'm thinking if instead of alpha a square, if it was alpha a minus 1 square, you would be kind of restricting your line in
So a minus
1 square. So that will be like you are trying to put the line in between. I mean, it's neither biased towards the towards
so
bending.
it turns out there's this result which I'm not going to actually prove, but is this really counterintuitive result that if you added this bias, which is really shrinking, it's really a shrinkage estimate. You're shrinking towards what the mean of the x coordinate is with all your estimates. You're actually going to introduce bias, but you're going to improve the overall error. Under a model where you built the data on a subset of it and you tested on the rest, there's always going to be some alpha under which this will perform better than alpha equals to zero. Or maybe there's like some special cases where the right one is alpha equal to 0, but in general, there's going to be some other one which is going to be the best one. That will give you a better expected fit. Unless your data lies exactly on the line, you're going to be better off for some alpha parameter. I didn't say what alpha parameter, but there's some alpha parameter where this will give you a better estimate. This is a pretty counterintuitive thing, but there's this idea of like regression towards the mean, and that's really what's going on here. So if people heard of regression towards the mean, so like if you give students who have some, every student is given with some sort of innate ability to do well on a test, and you give them a midterm and then you give them a final. On the first, and let's say every student is equally talented, right? So they're all. It's an expectation they're going to get the same grade, but maybe they, the grades are not going to be, there are going to be some noise around the average grade. Say the average grade was 80% on the first test. Some students are going to get 100, some are going to get 60. Well, if they all have the same ability on the second test, you would kind of expect them to, you somewhat expect them to regress towards their average. This is maybe not the best example. This is it's kind of a tricky concept from statistics. But this Tikhoff regularization is regressing the slope towards the mean. And so if you did the same trick where you lifted this to a higher dimension, and then instead of alpha a squared here, you had this as a vector, this was the vector squared, then you can do this with the average value as well, which is the coordinate, the value of all ones. And that's also going to kind of bring that estimate back towards the mean. It's going to bring it back towards 0. And it's strange that it brings it back towards 0, but the idea is that your errors are going to be really far in one direction or the other. And they might be really far one way, they might be really far the other way, but they're probably not going to be, right at 0. So you kind of want to bring your estimate back towards 0.
How do you know that this method gives you a better estimate? I mean, what is the quality estimator of your estimate?
Yeah, so it's not, it differs on how much better it is, so I'm not going to, I forget exactly how the proof goes of this, so I'm not prepared to go through why. And it's probably better to show, you can show this just for looking at the mean. If you're calculating the mean of a set of points, you want to use the mean as an estimator. You want to use some kind of, some penalty term on the mean. And it's not clear what the alpha should be. It says there exists some alpha for which this is true. So you then need to do cross validation to kind of figure out what the best alpha is. But if you do cross validation properly, that will give you a better estimate. So this is known as the Tikhonov regularization. So actually, there's some dual formulation of this, where the L to A, so it's going to give you the same, so let's say the R min of A, of L to A, L to alpha here, is going to be equal to the same as the R min A of the L2 cost. And instead of adding this regularizer, we're going to say such that, so this is such that is going to be less than some value gamma.